Okay, picking up with section 2.5, this is video part 2. I had gotten cut off when we were talking about the cost in dollars of building a house that is A feet squared in area. And so we were at part E. What are the units for f prime of 2000? So the derivative of cost with respect to area has units, dollars per feet squared. Okay, what is the real world meaning of f prime of 2000 equals 150? So we're talking about that 2000 representing an area in feet squared, and the 150 is representing, derivative of cost with respect to area is 150, so that's $150 per square foot. Okay, so for a house with an area of 2,000 square feet, the cost is changing at a rate of $150 per square foot. For a 2,000 square foot house, the cost is changing at a rate of $150 per square foot. Okay, so more interpreting of the derivative. Here we have the function y equals negative x squared. We have its graph here. So here's the function. It's a negative parabola centered at the origin. Here we have the graph of its derivative. All right, and here we have the graph of the second derivative. So this derivative graph of the derivative graph. All right, so let's take a look at each of these three graphs and how they relate to each other. So notice on the original function, it's a negative downward opening parabola. And we're going to look at three different intervals, or two intervals, I should say. When x is less than 0, f of x is increasing. The y values are increasing to the left of 0. Now, what does that mean about our derivative? Okay, that means the slopes are positive. So here you see y values on the derivative are positive. Okay, going back to our original function, when x is greater than 0, the function is decreasing. For these x values, the y values are going down. What does that mean about the slope? Okay, well, the slope of the function f of x is negative, and so you see that stated here. When x is greater than 0, f prime of x is negative. Notice that the y values of the derivative are negative y values, referring to the slopes of the original function at particular points. Okay, now f of x is always concave down. Okay, so it's opening downward. So remember, concave up, the graph will look like this. Concave down, the graphs will look like this. Okay, so f of x is always concave down, and you'll notice the second derivative. I'm just going to change some colors here. Concave down. The second derivative is always less than 0. Okay, so here's our second derivative function. It happens to be a linear function, constant, I should say. All right, and it represents the slope of the first derivative. So it looks like this first derivative was a negative linear equation or linear function. It would have a constant negative slope. The second derivative indicates a constant negative slope, maybe -2. All right, f prime of x is always decreasing. So when f prime of x is decreasing, our function will be concave down. All right, let's take a look at some values of the slope of the tangent line at particular locations on our original function f of x. Okay, so at -2, maybe the slope is +4. Right, +4 out here. Fix that. Okay, so slope here might be a +4. At -1, we'd be at a +2. At 0, slope of 0. At +1, a -2. And at +2, a -4. Okay? So our slopes go from 4 to 2 to 0 to -2 to -4. These numbers are decreasing, always decreasing, which implies our function is always concave down. Okay. So just some observations. F of x is concave down, f prime of x is decreasing, f double prime is less than 0. Right? All of these kind of support each other in saying the same thing. Okay, so here we're going to take a look at our function f of x, our derivative f prime of x, and our second derivative f double prime of x. Okay, so our function f of x does change concavity. Where would you say it changes concavity? And remember, concavity has to do with concave up and concave down. So it looks like our graph is concave down, then at some particular place it changes and becomes concave up. Okay, so if we're looking along this curve, somewhere in here, I would say it changes concavity. I'm going to put a point there. Okay, so here our graph is concave down. Somewhere there's an x value where it changes, and now it's going to become concave up. All right, let's take a look at the second derivative. Okay, the x location where we change concavity, I'm going to say it's about 1.5. I'm just estimating that on the graph. All right, and let's take a look at our second derivative where it crosses the x-axis. Looks like it's about at x equals 1.5. Okay, and notice our second derivative here is negative. Remember from our last example, when the second derivative was negative, our graph was concave down. Okay, to the right of 1.5, f double prime is greater than 0. Okay, and notice our graph is now concave up. Okay, so when the second derivative is positive, our function will be concave up. When the second derivative is negative, our function will be concave down. Okay, let's take a look at f prime of x. And they've noted that f prime of x decreases and then increases. Okay, so they're just talking about our slopes are negative here. And then our slopes are positive here. Okay, again, where is the location where it changes from negative slopes to positive slopes? It looks like it's at x equals 1.5. All right, negative slopes correspond to negative second derivative. Positive slopes correspond to positive second derivative. Okay, so f prime of x is decreasing. then f prime of x is increasing. Okay, so we've talked about these three things, where f double prime changes from negative to positive, negative, 0, positive. That's where our graph changes concavity. In our case, it's concave down to concave up. Where f double prime of x equals 0, that is the specific location of the change in concavity, and we call that point on our function an inflection point. Okay, where f prime of x changes from decreasing to increasing, notice that's the same location where f double prime of x changes or equals 0. Okay, decreasing, increasing, that location is a 0. This location is like a minimum on our first derivative. It creates a 0 on our second derivative. Just like the maximum and the minimum value on our function created zeros on our first derivative. Okay, summarizing before this video runs out, if f prime of x is greater than 0 on an interval, then f of x is increasing. If f prime of x is less than 0 or negative on the interval, then f is decreasing. So that means y values are going down. Where f prime of x equals 0 on an interval, then f has what we call a horizontal tangent. And we sometimes refer to it as either a turning point. So for example, these would be turning points. We're going from increasing to decreasing or decreasing to increasing. But we could also have what I call a terrace point. So we still have a horizontal tangent, but for example, on this graph, we could imagine that right in here and right in here, there is a horizontal tangent, but we're still increasing and increasing, and here decreasing and decreasing. Okay, so here there's going to be a sign change from f prime greater than 0 to f prime less than 0 to f prime greater than 0, whereas here there's no change in sign. Okay, f prime is positive, f prime is positive, f prime is negative, f prime is negative. Okay, second derivative. When the second derivative is positive on an interval, our function, our first derivative, our slope, is increasing, and our function is concave up. When the second derivative is negative, then our first derivative is decreasing, and our function is concave down. If f double prime of x is equal to 0 on an interval, then f sometimes has an inflection point. Okay, and if there's a sign change, again, that inflection point is the location where we are changing concavity. Okay, I would like you to try to match the function graph with the second derivative graph. Okay, so just taking a look at this first one, I'm going to run out of time. We have second derivative is negative and then positive, so I know my graph has to be concave down, then concave up. So try to match the curves based on the second derivative to the function graphs.